Hello everybody, this is Salih Yılmaz and I'm going to start solution of a Porch for the support reactions, and the mechanical system is shown in here, and in this system we will see how the support reactions can be solved easily. And here, friends, we have our mechanical system and we have a triangular load loaded on the porch, and we have a point load at the tip. So how can we solve for the support reactions of this system? And here, let's start with the solution for the analysis of the system. We have support reactions at point A, and let me call these support reactions VA and HA. And this V means vertical and H means horizontal support reaction. And here we have a support at D, but I don't care about the support because the support D is connected to the system by a cable here. So because of the cable here, I can only proceed with the solution with the tension in the cable, that's T here. And instead of using T, I can consider the component Tx and Ty. That's a better way actually. And I can just skip the actual tension force here because Tx and Ty is actually representing the two components of the force T. So we have four unknown forces here, and we have some equilibrium equations to solve the system. And let me write down the equilibrium equations. We have sum of the forces in x direction equal to 0, and we have sum of the forces in y direction equal to 0, and we have sum of the moments around some point, I don't know for the time being, and the sum of the moments around some point should be equal to 0. So actually, which equilibrium equation I should start with is that here we have very nice equilibrium equations, but which one of those equilibrium equations I should start with? If I'm going to start with some of the forces in x direction here, what is going to be happen? We will have VA, HA, TX, and TY as unknowns, and I'll have only FX in my pocket. So for unknowns and one equation, it's going to be stuck here. It's the same for some of the forces in y direction as well. It's going to be stuck. And what else for moment equilibrium? If I'm going to write down the moment equilibrium for a proper point, I can be able to eliminate some of the moments. Here, if I'm going to use some of the moments around point A here, there is going to be no moment contribution for VA, and there is going to be no moment contribution for HA because HA and VA are passing through point A. Therefore, there is going to be no moments for those two support reactions, and that's the same for the cable reaction TY, because TY, the extension of TY here is passing through point A, and because of TY, there's going to be no moments as well. So only unknown reaction that causes a moment around point A is Tx. So by writing down the moment equilibrium around point A, I can just solve for Tx. So let me write down the equilibrium equation here. And before writing it down, let me put a sign convention here. These two directions here are the forces in positive direction. I assumed as this, and the moments in the counterclockwise direction is going to be assumed as positive moments, but the moments in clockwise direction are going to be assumed as negative moments. So here, the force Tx is rotating our system in the counterclockwise direction. So Tx is going to be considered as a positive moment, and the distance between A and Tx is 2 plus 3 meters, so it's 5 meters. So 5 times Tx is the moment caused by force Tx around point A. It's a plus force because it's counterclockwise, and we have point load here, 50 kilonewton point load, and the total distance between point A and the point load is just 3 meters, and it's causing a clockwise rotation on the system, so it's a negative one. So 50 times 3 meter is the force, and we have only triangular load left. And instead of using this triangular load, we can just use the resultant force, and the resultant force here is located on 1/3 distance of the total span length. So the total span length is 3 meters, and 1/3 of 3 meters equals to 1 meter. So its distance from the point A is just 1 meter. So one another thing, the triangular load causes a clockwise rotation on the system around point A, of course. So it's a negative force or negative moment, and the total resultant force is 1/2 because of triangular distribution. The maximum force, maximum magnitude is 20 kilonewton per meter, and its span is 3 meters. So this portion is resultant force here, and it's just multiplied by the moment arm, which is equal to 1 meters. So from this equation, we should write down it's equal to 0. So by just writing down the equilibrium here, we can easily come up with the solution that Tx equals to 36 kilonewtons. Since it's positive, I can easily see that my assumed direction is correct. It's a force directed to the left. So when I have Tx here, I can just write down T, because Tx equals to T times cosine 30, which is given angle in the question. So T is going to be equal to Tx over cosine 30. And from here, I can calculate T as 41.52 kilonewtons, and this assumed force is positive as well, and this means that the direction I assumed in the beginning of the question is correct. Just see the beginning of the video, because I just skipped T because I added the components Tx and Ty, and from this equation here I can easily calculate Ty, because Ty equals to T times sine 30, which is 1/2, and Ty is just half of the T, so T equals to 20.67 or 76, excuse me, kilonewtons. So the direction of the force is upward. So I have Ty, Tx, and now I can proceed with the equilibrium equations, I can either use sum of the forces in x direction or sum of the forces in y direction. I just choose sum of the forces in x direction, and sum of the forces in x direction is equals to 0. And let me write down sum of the forces in x direction. I have HA, and what else? I only have Tx here, and it's toward to the left, and it's a minus force because of my sign convention I just put at the corner. So it's HA minus 36 equals to 0. That means HA is going to be 36 kilonewton. Since it's positive, my assumed direction is correct, and sum of the forces in y direction should be equal to 0 as well. And here I have Ty, which is actually equal to 20.76 plus VA minus 1/2 times, 1/2 times 20 times 3 meters. This is the magnitude of triangular load. And I have 50 kilonewton tip loading, and the summation should be equal to 0. And from here, I can come up with VA that's equal to 59.24 kilonewtons. It's positive. That means my assumed direction is correct, and so it's an upward direction. And I just find out sum of forces in y direction, x direction, and I after the solution I come up with the HA, VA, and cable tension forces. So what else I have to do is that I have to check if my solution is correct or not. You can just stop here, but in order to be sure, I just suggest you to check your solution. In order to check your solution, you can just use another equilibrium equation. We have used sum of the forces in x direction, sum of the forces in y direction, and sum of the moments around point A, but we didn't use sum of the moments around another point. It's not rotating around point A according to our solution, but if we make sure that it's not rotating another point around another point, then we can be sure that our solution is completely correct. So I am going to solve the moment equilibrium around point, let's say, E. It should be equal to 0 because it's not assumed to be rotating around point A. It's not rotating around point A, so this equation should be satisfied as well. So what are the forces here? We have VA, which is 59.24 times the distance between point A, which is the application point of the force VA, and the distance between A and E equals to 3 meters. And so here is 3 meters, but VA is rotating the system in the clockwise direction, so it should be a minus moment. And we have no moment contribution for 50 kilonewton load. We have a moment contribution for the horizontal support reaction at A, HA, and HA is rotating the system in the counterclockwise direction, so it should be a positive contribution. And 36 times 3 meters, which is the vertical distance between HA and point E. And what else we have? We have the support, the components of the cable reaction, Tx and Ty. Tx is rotating in the counterclockwise direction, Ty is rotating in the clockwise direction. So Tx resultant, the moment caused by Tx is a positive moment. Moment caused by the Ty is a negative moment. So here we should have Tx as 36 kilonewton times here 2 meter is the vertical distance point between point C and E, and it's a positive moment, as I said, and we have Ty equals to 20.76, and the distance here between Ty and point E equals 3 meters. So I'm going to multiply it by 3 meters, and Ty is rotating in the clockwise direction, so this should be a minus moment. And what else I should add? The triangularly distributed load. It's rotating in the clockwise, not clockwise. The triangular load is rotating the system around point A in the counterclockwise direction. So it's a positive moment. So the magnitude here is 1/2 times 20 times 3 times the distance here between the resultant force and the point E is just 2 meters here. And if I'm going to multiply it by 2, it should be equal to 0. I just should have to question that. And if I'm going to add up those components of the moments, and I can see that this summation equals to 0. So this shows that my solution is correct. So friends, we have solved out support reactions for this simple system. If you like the video, you can just join our channel and see more other videos for the solution of static problems or mechanics of materials or structural mechanics problems. If you suggest some problems for those courses, I would be happy as well. And some of the selected problems will be solved in this channel. If you like this video, please like it and join our channel and tell your friends to watch our videos to learn structural mechanics or statics or mechanics of materials.